Thanks very much. I'm Chuck Trolka, and this is my partner, Tom Bregelman. We're, as the gentleman said, with GCA Equity Partners, and essentially we're both sponsoring this trip, and also we do financing for a variety of projects from real estate to electric technology. And in fact, with these particular gentlemen after the presentation, anybody who's interested, stick around and feel free to talk to us. We've got cards. We've got a website if you'd like to take a look.
Finding the first investor in any significant startup is the challenge. Who's going to be first? And Tom was first. He looked at what we were doing, made a number of visits to Australia, rounded up a group of investors here. They brought in, for due diligence purposes, a specialist group out of the UK who designed a test rig that they were prepared to sign off on tests. So we had to build the test rig to their spec before they would sign off on the tests. So Tom was the first into this technology, and that's led ultimately to a wind turbine project that will be in production next year.
So first of all, we started off with the T-Flux motor, and in the very early days, very soon we realised that it was commercially non-viable. So we came up with the dual stator idea, and essentially it used the same philosophy, which is effectively the magnets are wrapped, they've got a coil wrapped around them rather than just on one side. In this case, it's essentially like taking an electric motor, folding it in half and wrapping it in on itself. So essentially you get two air gaps. It's like doubling the amount of power you can get out of a package which is sort of this size. So that's the original T-Flux. This was the very first prototype that was actually built adopting the philosophy from this. And this is looking inside it. You can see how there's like windings on the outside and windings on the inside. And there's a rotor that goes down between it. It's a cup type rotor. And the magnets are actually embedded into the rotor that rotates in that area. Now, this technology is what's called embedded permanent magnets. In other words, they're not on the surface. They're actually buried inside of the rotor. They're structurally very strong because there's no problem with them flying off. And they have, as people are probably aware, they're much less likely to demagnetise under heavy loads. This was the wind turbine generator. What the task was to translate this from a tiny little unit to a big unit, this size. And the technical challenges were quite high. Mainly, the biggest reason, all of the winding techniques were just copied. But then we had to solve the problems of how do you cope with the tremendous magnetic forces that are involved with two stators sitting inside one another. And this is the thermal analysis. What we were concerned about is could we get the heat out of the inner stator? Now, because we actually had the stator was actually fixed on the inner there, and the heat transferred down to the outer casing. So you can see the heat pattern on the outside casing. These generators were essentially sealed. They didn't have any flow through them at all. Now, when we ran these, we got very good results. The temperature rise on the windings inside only rose about sort of 40, 50 degrees. And we're able to keep the magnet temperatures well under about 80 or 90 degrees. This is what the rotor looks like. You can see the magnets in there. They're all clamped together with bolts that hold it all together rigidly. So this is all held in place. Now, we were able to get quite high speeds out of this without any worry of the magnets throwing out or coming off. This ring around the outside supports the end of the rotor so it can't fly out. And then inside there's a support inside here. This is what the inside looks like. When you've got permanent magnet motors with very high saliency, you can do two things. One, you can do a technique called phase advance. Now, I don't know does anyone know what that is? Phase advance is? What they essentially do is when they actually run the permanent magnet motor, they shift the phase, it's like shifting the sensors forward. You'd think, oh, that's not much good. But what happens is it then starts to take advantage of the reluctance capability of the motor as well as the permanent magnet capability of the motor. Now, when we did some testing on the motor we were able to get a 2-to-1 increase in torque at very low speeds with the same current drain out of the motor. So we put 50 amps in, without shifting with that phase advance, we'd get 50 Newton meters. We put 50 amps in, we shifted the phase, we got 100 Newton meters out of the motor. So you can nearly double the actual starting torque of the motor for the same amount of current drain from the controller. It's quite an interesting technique, and we got factors of about 2 or a little bit more out of our designs. Now, we didn't, in that particular motor, we didn't rebuild it with increased saliency or anything, but we just looked at what we had. We've really pushed things to the nth that we've never ever found any loss of permanent magnet in any of the designs we've had. Because they're buried inside, they're actually 100 degrees out of phase with what you would normally use in a surface magnet. Therefore, the actual flux in the stators tends to reinforce the permanent magnet flux in the rotors rather than trying to kill it. And we think that using this technique, we've been able to build motors that are essentially about double the torque and power and energy density of any of the best that are currently around. The other part of our technology is we've been building 2-pole and 4-pole generators, basically. They're not twin stators, they're single stators, because when you get to 2 poles, you simply can't fit that configuration in. It just doesn't work. There's a mathematical formula, and that formula just won't work. The thing becomes enormously big in diameter, and it just doesn't work. So we then went back to a single stator construction, and these designs they look exactly like you would see out there now as a normal generator, about the same size, a bit shorter, because they're much more efficient. We've gone from typically a generator of that size will be about 80% to 82%. Some of them are lower than that. We're 95. So we can give you a 15% increase. And the effect of that is essentially instead of using you can go an engine size down and still get the same amount of power out of the units. They run much cooler. The temperature rise in the rotor in these ones we've been testing is about 5-10 degrees above ambient, and it never gets above that. So they're really low temperature, very high efficiency. So this technology, and we've actually been able to get the magnet volume down by a massive amount, in the designs, the way we've designed them. And it was all done in Maxwell. Basically, we built the thing in Maxwell, we ran everything in Maxwell, then we built the prototype, and it was pretty right. Now we are now using that same model to scale up to different sizes, and we're talking to generator people that use them. So, and you can imagine all the generators that you've got around there all have windings on the rotors. There's no windings on these new rotors. They're pure permanent magnet, and they do the voltage. They regulate the voltage within the magnetic circuiting in the rotor. So there's no voltage regulators. They're just as simple as an AC motor. Now that's what's coming. It's come out of this technology, basically.